All right, we want to take a look now here at rational functions. So we'll spend some time with getting some sketches of rational graphs. Now in a rational function, we're looking at the division of two polynomials, like we have in this example here for f of x, where we've got the numerator polynomial, some function p of x, and the denominator q of x, some polynomial function. Now we know q of x could not equal 0, right? It's, again, a fraction we cannot divide by 0. So we'll go ahead and make that restriction. As we talk about graphing it, we're going to talk about the key characteristics. Of course, with any graph, we like to talk about the domain. Right? The domain, of course, are all the real number values of x that satisfy this function. So all the numbers of x except for those that make the denominator become 0, which we'll exclude. And with those undefined values, we start to get into characteristics of the graph. So we'll be talking about holes that come from undefined values. All right? Also vertical asymptotes. And speaking of asymptotes are the key characteristics of rational graphs. And what asymptotes are imaginary lines that shape our graph. We have three types of lines, right? We have vertical lines, horizontal lines, and slanted lines. Well, these are our three types of asymptotes that we're looking for. Vertical asymptotes, horizontal asymptotes, and oblique asymptotes, or slant asymptotes. So with that said, I want to start off with focusing on how to find or determine whether a rational graph has a hole in it. And the hole is just a simple point, an ordered pair of discontinuity. It's a break in our graph, an ordered pair which our graph jumps over, undefined location. And vertical asymptotes, again, are equations of vertical lines that shape our graph. What will happen is our graph will go vertical at those locations. It'll get closer and closer and closer to them. But it won't touch them because they're going to be an undefined location. And you'll see why as we look at vertical asymptotes and their characteristics. It says when looking for vertical asymptotes and finding these vertical line equations, we want to make sure we've factored the polynomials in our fraction. So in our rational function, make sure we factor the numerator, denominator polynomials, and see if we can reduce it, because that's important. Make sure we simplify the given rational function. And once we do, as we've simplified down to our simple form, we're going to look at the zeros of the denominator, and that'll lead us to the vertical asymptotes for this rational graph. Now, I want to take a look at this first example here. Let's take a look at example A. Now, in this example in f of x, we have a quadratic polynomial function, x squared plus 2x, in the numerator, and a quadratic polynomial in the denominator. Well, let's go ahead and factor these two quadratics. Now, in the numerator, we have a greatest common factor of x. All right, we have an x in both terms. So let's factor out that x. As we do that, we're left with an x from the first term and a 2 in the second term, right? We know x times x plus 2 are the two linear factors for this degree 2 quadratic polynomial, right? X times x is x squared, x times 2 is 2x. So we factor the numerator. Now, the denominator is a quadratic trinomial, and we can easily factor it. I'm going to go ahead and build its two linear binomial factors that it has. This quadratic. We need a x and an x up front for the x squared term. And we know our goal, right, we're factoring quadratic trinomials, is to find factor combinations of 12, right, that would work together to make this middle term coefficient of negative 4. So we know with that said, we would need a 2 and a 6, right? That's a factor combination of 12. 2 times 6 is 12. And we can get negative 4 from that, right? We know that 2 minus 6 is negative 4. So let's build that. So we need a plus 2, and we need a minus 6, right? And we could check that, right? The outer product is negative 6x. The inner product is 2x, and they add up to negative 4x. Of course, 2 times negative 6 is negative 12. So we see the two linear factors. Well, that's important because now you notice we have in this problem a common factor showing up of x plus 2 in the numerator and denominator. So this rational function does reduce. It reduces down to x divided by x minus 6. Well, that's important. This common factor that we just divided out of this function, and again, our function is now simplified to x over x minus 6, leads us to what we call a hole in our graph. Right? And we can have more than one hole. Now the holes come from the common factors. They're going to come from the zeros of the common factors. So I'm going to make a note of that. The zeros of your common factor, or factors, depending on how many you have. All right. And with that said, our common factor, it was x plus 2. Well, when does it equal 0? It equals 0 when x equals negative 2. So we have a hole in our graph at negative 2. Now, what's the y value? What will y equal? So we do need to find y. So to do that, we'll go evaluate our function at an input of negative 2. So f of negative 2 would be negative 2 divided by negative 2 minus 6, which is negative 2 over negative 8, which reduces to 1/4. So y equal 1/4. So our hole, we've got our hole now, and I'll put it in a different color. We know when x is negative 2, we have a y coordinate of 1/4, or 0.25. But there's a hole in the graph of this rational function, right? F of x. So with that said, we've got a hole, and again, we found that ordered pair. Now, can we find any other information? Well, we've got a point of discontinuity. So we know at negative 2, we're going to have a break in our graph, and the graph's going to jump over that point, that ordered pair. And we'll see that when we graph it. Now, let's also go to the vertical asymptotes. So after we found out that we had a hole at negative 2 on the x-axis, right, let's see where our graph goes vertical, if any. All right, vertical asymptotes. Remember, asymptotes are equations of imaginary lines, so we're looking for an imaginary vertical line that will shape our graph. And how to find them? The zeros of your remaining denominator factors. So again, we've already reduced it. Now our only denominator factor is x minus 6. So x minus 6 equals 0, right, when x equals 6. So that means we have a vertical asymptote at x equal to 6. And again, x equals 6, equation of a vertical line, right, in which our graph will go vertical, will be a break in it. So we're building this graph, right, just to show you again how to start to sketch it. And we can slide this down and give a little more room. Right, we go ahead and build in our x and y axis, right, and we would go ahead and show that. So here at 6, and I'm going to put that here in blue, right, and we'll put that in blue. So over here at 6 on the x-axis, I'm going to draw in this imaginary vertical line, all right, and with that said, that's the vertical asymptote. And then at negative 2, I'm going to put in the hole, negative 2 on the x-axis, left 2, up 1/4. We'll have a hole in our graph at that ordered pair. Graph will jump over that point, be a hole in it. Now with that said, that leads us to our domain. So when you have your holes in your vertical asymptotes, you can go ahead and write out the domain of your function. And again, domain are all the real number values of x that's satisfied. So all real numbers except negative 2 and 6. So graphically, we're going to see our graph, and we could shade it in. We'll shade it over here on the x-axis. Now we won't have anything at negative 2, be a hole there. But we'll see 3 different regions. So all real numbers less than negative 2, parentheses, all the numbers between negative 2 and 6, between the hole and the vertical asymptote, and then from 6 to infinity. So there's the domain. So remember, domain ties in directly with your holes and vertical asymptotes. Now to add to it, I want to go to looking at finding more information. Well, to do that, I'm going to look at horizontal asymptotes. So horizontal asymptotes are equations of horizontal lines that shape our graph. Well, we can have up to one horizontal asymptote. And to find that, we're going to be looking at the degrees. All right, let's go ahead and look at this example here. We have two polynomial functions, one of degree n. Remember, degree are the exponents from our leading term, the greatest power in a polynomial. Find the degrees of your two polynomial functions in your rational. To have a horizontal asymptote, your degree has to be either less than or equal to. If n is less than m, so if numerator degree is less than denominator degree, we're going to have a horizontal asymptote at the x-axis. The horizontal line y equals 0. If the degrees are equal, we're going to find the leading coefficients of the two polynomial functions. This example is a sub n and b sub m, and we're going to find the ratio of those two numbers. So a sub n divided by b sub n will be the location of your horizontal asymptote if the degrees are equal. And if n is greater than m, there is no horizontal asymptote. So if we look back at our example, let's go back to this one and let's compare the degrees. So you can see in this rational function, right, as we're looking at our horizontal asymptote, let's go ahead and write that down here. Horizontal asymptote. And again, in finding that, so writing down our notes, we want to compare the degrees of the two polynomials that you're dividing. So again, let's let n be the numerator degree. So n equaling the numerator degree, we'll abbreviate. Again, the greatest power, right, in your numerator polynomial, which again is the exponent of your leading term, which in this problem is 2. And m, we'll let m reference the denominator degree. And again, that's the greatest power, right, in your denominator polynomial. The exponent of your leading term, which in this problem is also 2. So in this example, n is equal to m. So if n equal m, we have a horizontal asymptote. It exists. And where does it exist? It exists at the ratio of the leading coefficients. So what are the two leading coefficients of these two polynomials? Let's look back at the beginning. Right, you see them right here. They're both 1. So the ratio of those two numbers, 1 to 1, we've got the horizontal asymptote of y equal 1. So our graph is going to flatten out horizontally at 1. So that's another piece of information that we could graph in here. So at y equal 1, let's go ahead and graph in that line. Let me erase this hole here. All right, at negative 2. We can draw that back in later if we need it. But here at y equal to 1, there's 1. Let's draw in this imaginary horizontal line at y equal to 1. So there's our horizontal asymptote. So again, shapes our graph. We have a vertical at 6. We have a horizontal at 1. Now, we would also want a little more information to begin sketching it, and that's where intercepts come in. So let's go ahead and talk about finding the x-intercepts and the y-intercepts. So these are quick points that we can get. How about our x-intercept points? Now the x-intercept's easy to find for any function, right? If we want to find out where our graph's sitting on the x-axis, we'll set our function equal to 0, right? So again, when does f of x equal 0? That's our question. So in this problem, we're looking at our rational function, which is what? We've reduced it to x over x minus 6. When does it equal 0? Well, as we were to solve for x, right, all we're doing is taking the numerator and setting it equal to 0, right? If fractions equal 0 when the numerator equals 0. So you end up getting, what, just x equal to 0. So that means we're going to have an x-intercept at the origin, 0, 0. So there's a x-intercept point. So here's a point in which our graph will pass through, right, our x-intercept point. So set your function equals 0. So one thing I'll make note, we can put in our notes, x-intercepts will be the zeros of your numerator polynomial, right, in any rational function. Make that example. So find those zeros. You simplified it down to one fraction. Now, how about the y-intercept? All right, where's this graph going to cross the y-axis? Well, we know 0, 0 is a y-intercept point, right? Well, again, showing it algebraically, we want to find the y-intercept, we let x equal 0, right? So that implies find f of 0. F of 0 equals what? That's, again, the algebra behind finding the y-intercept for any type of function, let alone a rational function. So what is f of 0? So in this problem here, f of 0, as we would plug it into our function, we get 0 divided by 0 minus 6. Out went x, in went 0. And you can see, of course, that is 0. So yeah, our y-intercept is the point 0, 0. So our y-intercept, x-intercept, nothing new as far as additional point to add to it. But with our graph, I can start to see what's going to happen with this graph just based off this information. Now, one thing I want to know about the horizontal asymptote is, will our graph intersect it? Will it cross it? And all you have to do to find that, to find out where we have any intersection, so I'm going to add this to it, intersection with the horizontal asymptote, because the horizontal asymptote is not an undefined value. Well, what we're going to do is we'll set our function equal to, so x over x minus 6, we'll set it equal to the horizontal asymptote, which is y equal 1. So when will it equal 1 is our question. So let's do that. Let's find out when it equals 1. Well, we do that. We solve x. We multiply both sides by x minus 6. Those cancel. We end up with x equal to x minus 6. And we were solving for x. We get 0 equal negative 6. So we get no solution, which implies there's no intersection. So the graph will never touch, right, this horizontal asymptote. So with that said, that's helping me with my graph. Now I could already begin graphing the left side. So based off that information, we know our graph flattens out at y equal 1. We know it won't touch the hole at negative 2. Going to pass through the origin, right? And then what's going to happen as it approaches x equal to 6? It's going to go vertical. Get closer and closer and closer to that vertical asymptote. So I've already got a picture of the left end of this graph just using what I found here. Now again, make note, we have a hole here at negative 2. So that's that ordered pair, negative 2, 1/4. Now how about to the right of 6? What does the graph do? Now that's where you'd want to find an additional point, right? And we could plug in any point, right? For example, what happens when x equals 7? So let's find another point. What is this value of this function? What's f of 7? Well, that would be 7 divided by 7 minus 6, which is 7 divided by 1, or 7. So that means when x is 7, y is 7. So that means we have a ordered pair of 7, 7. So we could plot that point, right? When x is 7, y is 7. So as I plot that, so it'll be up here somewhere on the quadrant 1, I'll plot in that ordered pair on this function. And that gives me now enough information to graph in the right end of this graph. And remember, this horizontal asymptote, this vertical line at x equals 6, a graph will never touch that. It'll get closer and closer and closer to it. It'll look like a vertical line at that location. And then what happens here at, let's erase that. What happens is we approach the horizontal asymptote. We know it ain't going to ever touch it. We've already shown that. It's going to flatten out horizontally. So these asymptotes are like magnets, pulling our graph right to it. Get closer and closer and closer to these imaginary lines, but they shape our graph. So that's a good example of a rational function, how to find its characteristics, right? And you could check it. You can put it in your TI calculator if you wanted to graph it and check it.